modeling with exponential function. The whole reason we learned exponential. In nature, most things grow you can model most things using exponential function. So it is a very useful tool to have. For this section, you may want to have your calculator handy, ideally a graphing calculator. Let's talk about the exponential growth, and here we're talking about the doubling in time. If the initial size of the population is n0 and the doubling time is a, then the size of the population at time t is modeled by this equation n of t equal n0 times 2 to the exponent of t divided by a, where a and t are measured in the same unit, so year, second, minute, and such. Example 1. Certain species of bird was introduced in a certain country 25 years ago. Biologists observed that the population doubled every 10 years, and now the population is 13,000. What was the initial size of the bird population? So let's lay down what we are given. So let's make a list of what we are given. We are given t is 25. It doubles in every 10 years. So a equal 10. Now the population is 13,000. So n of t equal 13,000. And we asked to find, in part A, the initial size of the bird population. So n0. So let's go ahead and use this formula that we have. So we know n of t equal n0 times 2 to the t divided by a. So then we have 13,000 is equal to n0 times 2 to the 25 divided by 10. So let's simplify this. 25 divided by 10 is 2.5. So here we can see that n0 is equal to 13,000 divided by 2 to the 2.5, and that is 2,298. So in the beginning, we have 2,228 birds, approximately. So part B, estimate the bird population 5 years from now. Okay, so now I have the equation. So now, in this case, we are given n0 equal 2,298, a equal 10, t equal 5, and we ask to find n of t. So n of 5 is equal to 2,298 times 2 to the exponent. So look, it is 5 years from now. Five years from now. Well, now was 25 years ago to start with. So actually t that given here is t equal to 30. That is the 30 year. From the time the bird was introduced to the island. So we're actually looking for n of 30. Okay. So 2 to the 30 divided by 5, that's 2,298 times 2 to the 6, and that is and that is 147,072. So 5 years from now, that is the population of the bird. So part C, we want to get the graph of the bird population. So let's come up with the equation so we can graph. So n of t equal to the initial population times 2 to the t over 10. Okay. So let's get this graph, and we use the graphing calculator for this. Since I already know where the graph starts, so maybe if I go ahead and adjust in the window on the graph, the graph will come up faster. Okay. So I'll go ahead and adjust in the window as follows. I will change the x minimum to 0, max to 40, and make the scale of 10. Y minimum of negative 50, just because, well, the bird population cannot be negative, but we want to just include that. And the max is 20,000 with the scale of 1,000 for each step. And so I go ahead and sketch the graph, and this is what I got. Okay. And so this is our graph. Let's take a look at the initial intersection. We can calculate a value. See what happened when x equal to 30. That is y. When x equal to 25, that's why it's about 13,000. Okay. So when x equal to 0, that is the initial population that we start with. So we're looking at the graph looking like that, starting as 2,298. 25 years later, let's say we're looking at 13,000. So we have an exponential graph, an exponential growth, or somewhere like that. Okay. Let's talk about the exponential growth in the relative growth rate. A population that experiences exponential growth increasing according to the model n of t equal n naught times e to the rt, where n of t is the population at time t, n naught is the initial size of the population, r is the relative rate of growth expressed as a portion of the population, and t is in time. In 2000, the population of the world was 1.6 billion, and the relative rate of growth was 1.4% per year. It is claimed that the rate of 1% per year would make a significant difference in the total world population in the fifth decade. Test this claim by estimating the population of the world in the year 2050 using the relative rate of growth of 1.4% per year and 1% per year. Okay, so part A. So we are given n of t. We are given that N naught equals 6.1 billion. R equals 1.4%, and that is 0.014. T is the population in year 2050, so T equals 50. Okay. So let's calculate this. So N of 50 is equal E equal N naught, that's 6.1, times E to the 0.014 times T, and that is that is 12.3 billion. Okay. For part B, we know that N naught equals 6.1, R equals 1%, and that is 0.01. T also 50. So N of 50 here in this case equals 6.1 times E to the 0.01 times 50, and that is that is 10.1 billion. So just looking at these two numbers, the difference here is 2.3 billion. That is a lot of people on Earth. So it definitely makes a difference if the relative rate of change is 1% instead of 1.4%. Right? So part B, let's go ahead and take a look at the graph. And we want to plot both of them on the same window. So the first one is 6.1 e to the 0.014 times t. The next one is 6.1 times e to the 0.01 t. And take a look at our window. We change it to back to normal. So x min is still 0, max let's say 20. Let's scale up 5. Y min, we can't have negative people, so start with 0. And let's make this 200. So we want to graph the population for the next 100 years. So x max need to be 100. So just for the sake of make it look easier to look at on the graph, make it 120. And let's go ahead and take a look at this two graph. So as you can see in the graph of so the red one is when we're looking at the relative rate of rate of growth is 1%. So it is a significantly less than the 1.4%. Let's go to the next one. Okay. The population in the city was 112,000 in 2014, and the observed doubling time for the population is 18 years. Find an exponential model using the first formula in this section, and we want to find another exponential model using the relative rate of growth formula, and then we get the graph of the population. Then we will estimate how long it takes for the population to reach 500,000. Okay, start with part A. Well, we are given n naught equal 112,000. We are given A equal 18. And we want to write up the equation. Okay, so then the equation n of t is equal to in part B, we are given n naught equal okay. So we know n naught, we don't have r. So how do we figure out r? We use the fact that the initial population was 112,000 and the doubling time is 18 years. This meant in 18 years, we're looking at 224,000 people times e to the r of 18, right? So now we need to figure out r. So this is 2 equal e to the r times 18. Solve for r. Now I can write the equation for n of t, then equal the initial times e to the 0.04t. In part B, we want to get the graph of the population as time t. I will leave that part to you to use with the graphing calculator. So let's estimate how long it takes for the population to reach 500,000. Let's say if we use the first formula, 500,000 and we need to solve for t in this case. And here we need to use log. And we solve for t. So the population will double in about 38.9 years. And let's see what happens if we use the other formulas. and we take ln both sides here. So t equal and that is about 37.4. Okay. So there is the discrepancy here due to the rounding of the relative growth rate. So when you do this type of problem, pay attention to how many decimal place you need to round to. In this case, I didn't specify what decimal rate to round to, so I usually round to 2 decimal places.